You are strapped into a seat leaving Earth at a fraction of the speed of light. The engines stop. The stars ahead bunch into a tunnel of blue fire. Behind you, home shrinks into a single pale dot, and the last radio signal from your family arrives already decades old. We're going to walk through the engineering of leaving forever. A fuel tank the size of a small city. A warp bubble that cuts you off from causality. A grandchild born on the ship who has never breathed Earth air. If the cold math of getting there fascinates you, subscribe, because this journey only gets harder. Strap in. Countdown begins. The moment your engines light, a countdown begins that nobody on Earth can see. You're the one watching it happen. Picture the ship accelerating out past the moon's orbit. Mission Control sends a routine check-in. The signal travels at the speed of light, which feels fast when you're standing on a planet, but starts to feel painfully slow the moment you leave one behind. At first, the delay is measured in seconds, then minutes, then, as your ship climbs past the orbit of Mars, hours. Somewhere past Jupiter, a flight engineer notices something nobody prepared her for in training. The delay is not just growing, it is growing faster than it should. That extra drag is the real starting gun of an interstellar voyage. It means you are moving at a speed where the universe itself starts behaving differently toward you. Every signal Earth sends has to chase a target that is running away at a fraction of the speed of light. Every signal you send back has to crawl across an expanding gulf. A simple question, asked and answered, now takes a full working day. Engineers at NASA's Deep Space Network already live in a mild version of this nightmare. When the Voyager probes phone home from roughly 15 billion miles away, the one-way signal takes more than 22 hours. A real-time conversation is impossible. Commands are queued, sent, and then the team waits almost an entire day to find out if the spacecraft even heard them. Now multiply that by thousands. At 1/10 the speed of light, which is the target velocity for serious interstellar studies like Project Daedalus, a trip to the nearest star system takes roughly 43 years. Your signal home near the end of the trip takes over 4 years one way. Ask Earth a question on a Monday. Your great-grandchild might get the answer. The crew quickly realizes the word conversation has to be retired. Nothing sent from Earth is current. Every message is already a memory by the time it lands on the ship's receiver. A birthday greeting from your sister arrives on her next birthday. A news bulletin about a world election arrives after the winner has already served a full term. The mission planner's first brutal slide in the crew briefing is always the same. It shows 2 clocks, one on Earth, one on the ship, and a growing grey bar between them labelled lag. That grey bar is not a technical inconvenience. It is the moment you stop being a citizen of Earth in any meaningful, real-time sense. Psychologists studying long-duration isolation for Mars missions have already flagged what this does to human minds. At delays of 20 minutes, astronauts report feeling professionally orphaned. They start making decisions without asking, because asking is useless. They begin to trust the ship more than the planet. On an interstellar run, that feeling is not a phase, it is the permanent operating condition, and this is only day 1. You have not yet hit cruise velocity. You have not yet seen what happens to time itself when you push closer to the speed of light. The signal delay is the polite problem. The real surprise is waiting just a little further down the acceleration curve, where the clock on your wrist and the clock on your mother's kitchen wall start disagreeing about which day it is. Somewhere past the halfway point of the acceleration burn, the ship's chief engineer does a small experiment. She sets two identical atomic clocks side by side. Then she leaves one running on the ship and beams a ping to a reference clock back at mission control. The numbers come back. She checks them 3 times. Then she calls the captain. The ship's clock is losing time against Earth. Not because it is broken, because physics is doing exactly what Einstein said it would. Time dilation is the cold heart of every interstellar mission plan. Push a spacecraft fast enough and the seconds on board start ticking slower than the seconds back home. At a cruising speed of about 86% the speed of light, 1 year on the ship is 2 years on Earth. At 99%, 1 year on the ship is roughly 7 years on Earth. At 99.9%, 1 ship year equals more than 22 Earth years. These numbers are confirmed science. Atomic clocks flown on commercial airliners already show this effect at tiny speeds. GPS satellites have to correct for it every single second, or your phone's map would drift miles off course within a day. The physics is not a theory waiting to be proven. It is baked into the navigation you used to get to work this morning. Now scale it up to a starship. You, the pilot, shave in the morning, eat breakfast, run a systems check, go to sleep. A normal day. Meanwhile, on Earth, your nephew starts kindergarten, graduates high school, gets married, and names his first daughter after you. All in what feels to you like a month. The human body does not cheat the clock. The crew is not living longer in any useful sense. A 40-year-old captain who leaves Earth will still feel roughly 45 when she arrives at her target. Her muscles age at her own rate. Her memories form at her own rate. But when she beams a message home, the Earth that receives it has moved through a full generation. This is where the mission stops being a voyage and starts being an exile. The crew is not travelling across space alone. They're sliding forward through Earth's timeline one way with no break. Engineers have a dark nickname for the effect. They call it the widow's lag. The pilot feels she's been gone 6 years. The family has buried her parents, forgotten her middle name, and watched her old apartment building get demolished. The pilot is, in a very literal sense, a visitor from the past arriving in her own future. Now flip the equation. For the mission to matter, the ship has to eventually decelerate, which means it has to eventually turn around or land, which means the crew at some point has to decide whether to ever come back into Earth's fast-running clock or stay permanently in the slower ship time bubble, drifting ahead of their home civilization forever. That decision is not in the mission manual. It is a personal sentence signed the day they boarded, and the cruelest part of this physics is still hidden. Because once the crew accepts the time debt, another question pushes to the front of the cockpit. Who designed a ship that could only ever leave, and never, by any serious engineering proposal, actually turn back? In 2016, a group of the smartest physicists alive walked on stage in New York and announced a plan to reach another star within a human lifetime. Stephen Hawking was there. Yuri Milner wrote the check. The project was called Breakthrough Starshot, and on paper, it works. The pitch was simple and shocking. Forget massive rockets. Forget 50,000 tons of fusion fuel. Instead, build a tiny spacecraft the size of a postage stamp, attach it to a sail the thickness of a few atoms, and hit that sail with a ground-based laser array, powerful enough to rival a small nuclear plant. The light pressure pushes the sail pulls the chip. In about 10 minutes of laser fire, the probe is moving at roughly 20% the speed of light. At that velocity, the nearest star system is reachable in about 20 years, faster than any mission humanity has ever flown. A single human engineer could launch a probe in her 30s and still be alive to see the data come back. Then, an intern asked the obvious question. How do we stop it when it gets there? The room went quiet, because the answer is, we do not. The Starshock concept has no brake. The probe screams through the target star system in a few hours, snaps whatever pictures it can, and keeps going forever into deep space. It cannot orbit the planet it was sent to study. It cannot land. It cannot turn around. And this is not a quirk of one project. Every serious interstellar proposal on the table today runs into the same wall. Accelerating a spacecraft to a fraction of light speed is brutally hard. Decelerating it at the other end without a massive refueling station waiting at the destination is exponentially harder. You have to carry the fuel to slow down. That extra fuel has mass. That mass requires more fuel to accelerate in the first place. The math spirals into absurdity very fast. Light sails have one extra problem. The laser that pushed the sail is back home. There is no second laser array orbiting the target star, ready to shine backward and slow the probe down. You can only accelerate with a photon gun that is chasing you from behind. Engineers have floated clever workarounds. A magnetic sail that opens at the destination and uses the target star's own particle wind as a brake. A secondary fission stage that fires backward. A gravitational slingshot around the target star's planets to bleed off speed. None of these are proven. All of them add mass, cost, and new failure modes, and none of them help a human crew. A chip the size of a stamp can take the hit of zipping through a star system at 1/5 light speed. A human body would be paced. That is why Starshot's engineers are honest about what they are building. They are building a reconnaissance mission, not a colony ship. A scream into the dark one way carrying a camera and a prayer. If even the simplest probe cannot come home, what happens when mission planners try to bring an entire crewed vessel back to Earth? The fuel equation stops being rude. It starts being murderous, and the number it spits out is the reason every serious Starship study on record has quietly written the word return in pencil, then erased it. Inside the archives of the British Interplanetary Society, there's a stack of binders most people have never seen. One of them is labelled Project Daedalus, another is labelled Project Icarus. A third, from NASA and the Naval Research Lab, is labelled Project Longshot. Together they represent the most serious peer-reviewed attempts ever made to engineer an actual interstellar voyage. Open any one of them, flip through the mission profile, find the section on the return trip. You will not find one, because there isn't one. Project Daedalus, designed in the late 1970s by a team of volunteer British engineers, was a two-stage fusion-powered probe aimed at Barnard's star. The crew count was 0. The payload was scientific instruments. The mission plan called for a 50-year cruise, a brief flyby, and then permanent drift into interstellar space. The designers stated in writing that a return trip was not within the capabilities of any technology they could foresee. They did not even try to design one. They called it a flyby mission and moved on. Project Icarus, its modern successor, kept the same philosophy. One way, probe only, no passengers. Project Longshot, a joint United States military and NASA study from 1987, was slightly bolder. It proposed sending a robotic probe to Alpha Centauri b using a nuclear pulse engine. Mission duration was roughly 100 years. Crew, again, 0. Return plan, again, none. The pattern is not an accident. It is a direct consequence of the fuel math, which we will get to in a moment. But it is also a philosophical choice that every serious interstellar planner eventually makes. You either accept that the mission is one way, or you cancel the mission. This is why NASA's own Breakthrough Propulsion Physics program, which ran briefly in the late 1990s, spent most of its effort on exotic concepts like warp drives and wormholes, because the team understood that ordinary, sane rocket science simply cannot give you a round trip to another star. If you want a return mission, you have to break physics, and breaking physics so far has not cooperated. Now, imagine telling that to a human crew. A team of astronauts trains for 10 years. They say goodbye to their families, they strap into a ship, and the mission commander reads them a final line from the flight plan that says, in effect, you will arrive at your destination older, greyer, and alone, and the ship is not coming back. There is no second ship in the pipeline to pick you up. There is no fuel depot waiting at Proxima Centauri. The agency that launched you will almost certainly not exist in any recognizable form by the time you land. Every astronaut who's ever flown to low Earth orbit came home. Every moonwalker came home. Even the Mars mission proposals, for all their terror, include a return stage. Interstellar travel breaks that expectation completely. It is the first class of human mission where going and staying are the same word. The question mission planners ask next is not whether humans would volunteer. Thousands already have for far less. The question is why the fuel equation, the oldest and simplest law in rocketry, keeps coming back with the same brutal answer. And to understand that, you have to meet the number that has haunted every rocket designer since the days of Tsiolkovsky. There is a moment in every rocket designer's career when they run the numbers for an interstellar mission and quietly close the laptop. It usually happens around coffee break, because what the spreadsheet spits out is not a rocket. It is a fuel tank the size of a small moon. The problem has a name. It is called the tyranny of the rocket equation, and it was written down by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903, long before anyone had even flown a plane. Tsiolkovsky showed that to make a rocket go faster, you have to carry fuel. But that fuel has weight. To lift that fuel off the ground, you need more fuel, and that extra fuel also has weight. The math compounds like credit card interest from hell. For a trip to low Earth orbit, the tyranny is manageable. A Falcon 9 rocket is roughly 95% fuel and 5% vehicle by mass at liftoff. That is why rockets look the way they look. A thin metal tube with a tiny capsule perched on top. Almost all of what you see thundering off the pad is propellant. Now try scaling that to interstellar speeds. To reach 1/10 the speed of light using the best chemical rockets ever built, the fuel mass required is larger than the observable universe, not larger than Earth, not larger than the solar system, larger than everything. The equation returns a number with so many zeros that physicists use it as a joke at conferences. Okay, so chemical rockets are out. Try nuclear fission. Better. A fission-powered starship could theoretically reach a few percent the speed of light, but the fuel mass still ends up in the millions of tons. Try fusion. Better again. Project Daedalus calculated 50,000 tons of helium-3 fuel, harvested from the atmosphere of Jupiter, just to push a probe to Barnard's star. Now here is the twist the public never hears. Every one of those numbers assumes a one-way trip. No braking at the destination, no return. If you want the ship to decelerate when it arrives, you have to carry enough fuel to slow down. That extra fuel has to be accelerated at the start, which means carrying more fuel to accelerate the braking fuel, which means more fuel still to lift that extra fuel. The tyranny stacks on itself. The rough rule of thumb among mission planners is brutal. A fully braked mission to Alpha Centauri requires roughly the square of the fuel mass of a flyby mission. If the flyby needs 50,000 tons, The braked mission needs something closer to 2.5 billion tons, and if you want a round trip, you square it again. At that point, you are no longer designing a spacecraft, you're designing a small planet that flies. Engineers have a cold joke about this. They say interstellar travel is easy, interstellar return is impossible. One is just engineering, the other is arithmetic. This is the real reason every serious Starship study comes back with a one-way mission profile. It is the reason Daedalus is a flyby. It is the reason Starshot has no brakes. The rocket equation does not care about human feelings, it just keeps multiplying. And somewhere in that multiplication, hidden in plain sight, is the wall that no amount of clever engineering has ever climbed. A wall made entirely of math. The rocket equation has a shape. If you plot it on a graph with spacecraft velocity on one axis and fuel mass on the other, it does not climb in a nice straight line. It curves, gently at first, then viciously upward, then it goes vertical. The vertical wall is where interstellar dreams die. Mission planners call it the exponential cliff. Up until about 10% of light speed, the fuel math is brutal, but theoretically tractable with fusion power. You can design a ship, you can sketch a trajectory, you can run a believable simulation. Past 20%, the fuel requirements climb so fast that every gram of added payload costs tons of propellant. Past 50%, the ship becomes mostly tank. Past 90%, the required fuel exceeds the mass of large asteroids. This is why no serious engineering paper ever proposes a chemical rocket for interstellar travel. It is also why even fusion-based designs top out at around 12% of light speed in their most optimistic versions. The wall is not a failure of imagination. It is a direct consequence of a 300-year-old conservation law. Momentum has to be conserved. If you want to throw yourself forward, you have to throw something backward. And the faster you want to go, the more something you have to throw. Engineers have spent a century trying to cheat this. Every known trick has been tried on paper. Staging the rocket the way Saturn V did on its way to the moon buys you a small bonus. Interstellar missions could in theory use dozens of stages instead of 3, but the gain flattens out fast. After about 5 stages, each new stage adds almost nothing to the final velocity. Using a higher energy fuel helps more. Jumping from chemical burning to fission to fusion to antimatter roughly doubles or triples your achievable speed at each step. But each jump comes with its own nightmare. Fusion fuel is scarce. Antimatter is the most expensive substance ever manufactured. A single gram produced by current particle accelerators would cost more than the entire annual budget of a major nation. And humanity's total global production of antimatter over decades of work amounts to roughly enough to boil a teacup. Then there is the so-called external power workaround. Leave the fuel at home, push the ship with a laser from Earth, or a particle beam, or a magnetic track. This is what Breakthrough Starshot tried. It is elegant. It dodges the rocket equation almost entirely. But it only works for tiny unmanned probes, and only for acceleration. Nothing pushes you back when you want to stop. The rocket equation, in other words, is a door that only opens outward. You can leave. You cannot return through the same door with anything resembling a human crew. Mission planners have a phrase for this predicament. They call it the delta V prison. Delta V is the engineering term for how much change in velocity a spacecraft can perform. Earth orbit is a low cell in this prison. The Moon is 1 floor up. Mars is 2 floors up. Jupiter may be 3. Alpha Centauri is on a roof so high the elevator cable has not been invented yet. And the staircase back down, the return delta V, is twice as tall. To break out of the prison, engineers have started flirting with ideas that do not so much solve the rocket equation as try to sneak around it entirely. One of those ideas involves the most explosive substance ever discovered, and it hides one detail that makes every planner's hand shake. Deep inside CERN in a Swiss laboratory under the Alps, a small refrigerated trap holds a few atoms of antimatter at a time. They are the most expensive objects on Earth. Gram for gram, they cost roughly $6 trillion to produce, and the global stockpile of antihydrogen gathered across decades of work amounts to about 1/1000th of a gram, and yet, on paper, antimatter is the most perfect rocket fuel ever conceived. The logic is almost unfair. When 1 gram of antimatter meets 1 gram of ordinary matter, both annihilate completely. 100% of the mass converts to pure energy. Nothing is left behind. Compare that to the hydrogen fuel in a conventional rocket, which releases about 1/1000th of its mass as energy. Or even fusion, which releases less than 1%. Antimatter is, energetically, the jackpot fuel of the universe. A single gram of antimatter, annihilating with a gram of regular hydrogen, releases roughly the same energy as the Hiroshima bomb. 2 pounds of the stuff would, in theory, propel a spacecraft to Alpha Centauri in 40 years. Mission planners have sketched the ships. The most detailed is a NASA concept called the Valkyrie, designed by physicist Charles Pellegrino and propulsion engineer Jim Powell in the 1990s. A long, thin spine of a vessel with a heavily shielded antimatter trap at one end, and the crew habitat as far away as possible on the other. The exhaust plume is not flame, it is a narrow, invisible beam of gamma rays. On paper, it works. In reality, the numbers break the mission before it starts. To send that 40-year Valkyrie to Alpha Centauri, engineers estimate the ship needs somewhere between 10 and 100 tons of antimatter. Current global production, running flat out through every particle accelerator on Earth, might manage a few nanograms per year. A nanogram is 1/1000th of a gram. At current rates, manufacturing the fuel for a single mission would take longer than the age of the universe. Even if production were scaled up by factors no engineer seriously predicts, the cost would exceed the global economy of every nation combined, many times over. Antimatter is not fuel. It is an economic black hole that happens to glow. And then there is the storage problem, which is where every antimatter engineer's nightmare really starts. Antimatter cannot touch anything. If one atom of it brushes the wall of its container, both annihilate and release a burst of gamma rays. So the fuel has to float, suspended in a magnetic trap, cooled to almost absolute zero for the entire mission. If the trap loses power for a fraction of a second, the ship does not malfunction. The ship briefly becomes a star. A reactor-scale antimatter containment failure would not be a spacecraft accident. It would be a small stellar explosion, visible from other star systems. This is the quiet horror of the Valkyrie mission profile. You're strapped in behind a fuel tank that, at any moment during your decades-long voyage, could convert you and your ship into a momentary nova. And the trap keeping that from happening is running on a power system that has to never, ever fail. If antimatter is the fuel that is too expensive and too dangerous to ever work, there is another candidate on the drawing board. One that runs on the same process that powers stars, and the only working design ever drafted weighs more than the Great Pyramid. In the basement of the British Interplanetary Society, a set of hand-drawn blueprints shows a spacecraft that looks less like a rocket and more like an industrial refinery tipped on its side. This is Project Daedalus, the most detailed fusion starship design ever produced. The team that built it in the late 1970s included some of the best propulsion engineers in Britain. They worked nights and weekends for 5 years. What they produced is still considered the benchmark for every fusion Starship study that followed. The ship is 54,000 tons at launch. For comparison, the International Space Station weighs about 420 tons. A Saturn V moon rocket fully fueled weighed roughly 3,000 tons. Daedalus is nearly 20 Saturn Vs stacked together. Almost all of that mass is fuel, specifically pellets of deuterium and helium-3, each about the size of a marble. 50,000 tons of them, packed into 2 massive spherical tanks that form the bulk of the vehicle. The engine is the strange part. It is a magnetic nozzle, a kind of invisible funnel shaped by powerful superconducting coils. Every second, the ship fires 250 fuel pellets into the focus of this funnel. Each pellet is hit by electron beams from 40 different directions at once, crushing it into a microfusion explosion. The plasma blast is steered out the back by the magnetic field. 250 tiny suns going off every second channeled into a thrust beam. For almost 4 years, Daedalus burns continuously. It accelerates to about 12% the speed of light. Then the first stage drops away. The second stage takes over for another 2 years. When it finally shuts down, the ship is cruising, fuel exhausted, toward Barnard's star. No crew, no return. Just a probe carrying cameras and instruments, designed to scream through the target system in a single afternoon and keep going into the dark forever. The engineering is brilliant. The problems are the kind that keep physicists up at night. Helium-3, the fuel Daedalus burns, is almost non-existent on Earth. A few grams per year are produced as a byproduct of nuclear decay. To fuel Daedalus, the designers propose skimming it from the atmosphere of Jupiter using a fleet of aerostat mining balloons. The mining operation alone would be a multi-decade industrial project larger than any humans have ever attempted. The engine has another problem. The magnetic nozzle, the thing that focuses the fusion blast and keeps it from vaporizing the ship, must survive 250 nuclear explosions per second for years. The team admitted in the final report that the exact materials for this nozzle did not yet exist. They sketched in what they hoped future metallurgy might deliver. And then there is the crew version of the calculation, which Daedalus never even attempted. If you want to put humans on this ship, you need life support, shielding, habitat volume, food, water, and enough fuel to slow down at the destination. Every one of those additions by the logic of the rocket equation squares or cubes the total fuel mass. A crude Daedalus would not weigh 50,000 tons, it would weigh millions, possibly billions. Fusion might get us to the stars, it will not get us back. And when engineers tried to find a way to cheat even this number, one of them looked at a passing cloud of interstellar hydrogen and wondered, what if the fuel is already out there, waiting for us to catch it? In 1960, an American physicist named Robert Bussard proposed the most elegant interstellar engine ever sketched. It solved the rocket equation in one stroke, and for about 30 years it was the favourite dream of every Starship engineer who ever looked up. The idea is almost too clean. Space is not empty. Between the stars, thin clouds of hydrogen drift through the galaxy, about 1 atom per cubic centimetre on average. It is a vacuum by any normal standard, but across the volumes a starship traverses, those atoms add up. A vessel crossing trillions of miles passes through an enormous quantity of free hydrogen. Bussard's insight was this: what if the ship did not carry its fuel? What if it scooped up hydrogen from interstellar space as it flew, fused it in a reactor and blasted the exhaust out the back? A giant electromagnetic funnel, miles wide, opens at the front of the ship. It ionizes the passing hydrogen and pulls it into a central fusion chamber. The reactor fires continuously. The ship accelerates forever, with no fuel tanks, no mining operation, no Jupiter refinery. On paper, the Bussard ramjet could reach speeds close to the speed of light, given enough time. It could, in principle, cross the galaxy in a human lifetime thanks to time dilation. Science fiction authors fell in love with it. Larry Niven, Paul Anderson, and many others built entire fictional civilizations around fleets of these ships. For a while, NASA took it seriously enough to fund preliminary studies. Then the physics got meaner. In the 1980s, a physicist named Robert Zubrin ran the numbers on the scoop itself. He asked a simple question: how strong is the drag force on a magnetic funnel moving through interstellar gas at relativistic speeds? The answer destroyed the dream. At high velocity, the scoop does not act like an intake, it acts like a parachute. The faster the ship moves, the more hydrogen it plows into, the more electromagnetic drag the scoop generates. Beyond a certain speed, the drag exceeds any thrust the fusion engine can produce. The ship stops accelerating. It starts slowing down. The magnetic scoop becomes, in effect, an enormous interstellar brake. Zubrin's calculation showed that a Bussard ramjet, far from being a near light-speed engine, would top out at a few % of light speed at best, and that was assuming the fusion reaction it depended on, the proton-proton chain that powers the stars, could actually be made to run inside a man-made reactor. To date, no laboratory on Earth has ever achieved it. That particular reaction is so slow, even in the core of a star, that it takes billions of years to complete. A ship trying to do it in real time would need reactor conditions far beyond anything physically possible. The Bussard ramjet, in short, is a beautiful broken idea. The scoop cannot keep up with the ship. The fusion fuel is the wrong kind of hydrogen, and the drag turns the engine into an anchor. Some engineers have tried to rescue variants of the concept, magnetic sails that use the same interstellar gas purely as a brake without any engine. Partial ramjet hybrids that only scoop during certain mission phases. None have been built, all are still paper, which means the ship that feeds on the galaxy itself is for now a myth. And the engineers who needed a way around the rocket equation looked elsewhere, to a paper from 1994 that did something stranger than propose a better engine. It proposed moving space itself. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that was only 6 pages long. It was titled "The Warp Drive Hyperfast Travel Within General Relativity," and it did something no propulsion paper had ever done before. It described, using Einstein's actual equations, a way to move faster than light without violating the laws of physics. The trick was not to move the ship. The trick was to move the space around it. Alcubierre showed that if you could warp the fabric of space-time itself, contracting it in front of your vessel and expanding it behind, the ship could ride a bubble of normal flat space through the distortion. Inside the bubble, the ship experiences no acceleration, no time dilation, no forces of any kind. It is just sitting still. But the bubble itself surfs through the universe at any speed you like. A ship could, in theory, cross from Earth to Alpha Centauri in a matter of weeks, as measured by everyone, including the crew and the people back home. The paper caused a genuine sensation. For the first time since H.G. Wells, a serious physicist had written down a warp drive that did not break Einstein. NASA's Eagle Works laboratory spent years trying to see if any measurable effect of the Alcubierre geometry could be detected in a vacuum chamber. Dozens of follow-up papers refined the math, then people read the fine print. The Alcubierre drive requires a substance called negative energy density. It is matter with mass less than zero. Not the absence of mass, actually negative mass. This kind of matter has never been observed in the universe. Small related effects like the Casimir force between two metal plates in a vacuum hint that quantum fields can sometimes have negative energy in tiny, fleeting amounts. But a warp bubble needs enormous quantities, sustained continuously, shaped into a precise geometry around the ship. Early estimates suggested the energy required was roughly the mass energy of the planet Jupiter, converted entirely into this exotic form. Later refinements by physicist Harold White and others brought the number down to about the mass of a large truck, still impossibly large and still in a form of matter that no human has ever created, measured, or even proven exists. Then the really ugly problem showed up: causality. A ship inside the warp bubble is, by construction, cut off from the rest of the universe. No signal can pass into or out of the bubble while it is moving faster than light. The crew cannot steer, they cannot abort, they cannot receive instructions, they cannot even see where they are going, because light from the destination cannot reach them through the warped region in front of the ship, and worse. When the bubble arrives at its destination, the contracted space in front of it releases all the energy that has been compressed during the journey. Recent calculations suggest this release would be a gamma-ray burst so intense it could sterilize everything in the path of the ship. The warp drive used by a species hoping to visit other worlds would arrive as a planet killer. A return trip requires building another warp bubble at the destination, which requires negative energy, which does not exist, produced by infrastructure that was not sent with the ship. The one-way problem, in other words, applies to warp drives too. If no fuel, no scoop, and no warp can bring the crew home, Starship planners eventually stopped asking about the ship and started asking about the crew. Specifically, whose crew? Inside a windowless room at Icarus Interstellar, a non-profit group of engineers and ethicists, there is a whiteboard that has been slowly filled over years. The top of the board reads Generation Ship Ethics. Below it, in a tight grid, are about 40 small boxes. Each box is a question. Some of them have answers, most do not. One of the boxes near the middle reads, Do we tell them they are on a ship? The generation ship concept is at first the cleanest solution to the interstellar problem. Forget the rocket equation, forget fusion, antimatter, warp drives. If a trip to the nearest star takes 200 years, then build a ship that can house a community for 200 years. The people who arrive will not be the people who left. Their great-great-grandchildren will. In engineering terms, the math relaxes enormously. The ship only needs to reach a few % of light speed. It can be big, slow, and heavily shielded. Designs like Project Hyperion, studied in the 2010s, sketched kilometre-long hollow cylinders that rotate for gravity, with farmland, forests, and towns inside. A closed ecosystem with a breeding human population of about 500, cruising through the dark for centuries. On the engineering whiteboard, it looks solvable. On the ethics whiteboard, it becomes horrifying. Because the people on Generation 2, Generation 3, Generation 10 never chose to be on the ship. They were born inside a metal cylinder moving at 50 million miles an hour. They will never touch a planet. They will never see a horizon without a wall curving up behind it. They will never stand in rain that was not manufactured by the ship's weather system. Their life their children's lives, and their children's children's lives are a project they did not sign up for. Philosophers have pointed out that this is a form of consent problem unlike any in human history. Every previous migration, however desperate, happened to people who were already born. The generation ship conscripts the unborn. Engineers at MIT and the British Interplanetary Society have tried to calculate the minimum viable population for such a mission. Early estimates suggested about 150 people. A 2018 study by anthropologist Cameron Smith raised the number to around 2,500 to avoid genetic bottlenecks over multiple generations. Other studies pushed it higher still, and then the darker questions surface. What happens if the crew, 10 generations in, decides the mission is absurd? Do they have the right to turn the ship around? To stop reproducing? To open the airlocks and end a project no one alive ever volunteered for? What happens when the ship's computer contains the entire accumulated culture of Earth, but the humans inside have forgotten how to read half of it? Studies of isolated human groups on Earth, like the Tasmanian Aboriginal population after they were cut off from the mainland, show that small communities can lose complex technologies within a few generations. The crew of a generation ship might arrive at their destination unable to operate the landing systems their ancestors built. The cruelest possibility is that they arrive and find the target uninhabitable. Centuries of confinement for a dead shore. The ship becomes a coffin with momentum, and there is an even stranger workaround that some engineers have started to prefer. One that avoids breeding humans in flight entirely by sending a crew that does not need to live through the journey at all. On the third floor of a research building in Pasadena, a NASA engineer named Adam Crowell once asked a question that made the rest of the room very quiet. What if the colonists are not awake yet? The concept is called an embryo space colonization mission. The ship launches with no living adults on board. Instead, the cargo is thousands of frozen human embryos, a small crew of humanoid robots, and an artificial womb facility built into the habitat. The entire vessel is a seed, dormant for the full duration of the voyage. It drifts, unmanned in the human sense, for a century or two. Then, as it approaches the target star system, the robots wake up. They check the destination. They assess the atmosphere, the radiation, the gravity. If the planet is survivable, they begin thawing and gestating the first generation of humans. The children are born to machines. Their first memories are of robotic nursemaids. Their first words are in a language the ship's computer has selected from a database of Earth cultures. They grow up on an alien world, raised by instruction manuals and artificial guardians, with no biological parents, no childhood stories, and no direct connection to the species that sent them. Engineers love the concept. It sidesteps nearly every problem of generation ships. No life support for adults, no food production for centuries, no mutinies, no genetic bottlenecks, because thousands of embryos provide vast genetic diversity from frozen storage. Mission planners at the British Interplanetary Society and Icarus Interstellar have calculated that an embryo ship could weigh a small fraction of a generation ship. The cargo, frozen at cryogenic temperatures, takes up a tiny fraction of the volume of a living community. The robots are rugged and expendable. The ship itself can be slow, which reduces fuel costs. The ethics professors, again, get nervous, because now you are not conscripting the unborn. You are manufacturing them on a world they did not choose, in an environment they did not evolve for, without a single human elder to teach them what it is to be human. Every cultural and biological link to Earth is severed. Anthropologists have asked what these children would even become. They would speak a language programmed by a computer. They would have no grandparents, no extended family, no community that predates them. Their religion, if any, would be the one the mission planners decided to load into the ship's archive 2 centuries earlier. Their history would be a file cabinet, not a living memory. There is also a cold engineering problem hiding inside the cold biology. Frozen human embryos have been successfully stored for about 30 years on Earth, with good thawing success rates. Whether embryos can survive 200 years, exposed to cosmic radiation, trapped in a ship that might suffer temperature fluctuations is completely unknown. No one has ever tested it. The first generation of colonists might thaw with chromosomal damage so severe that the mission dies in the nursery. And even if it works, even if the children grow up healthy and alert under an alien star, they will not be the first humans to arrive at another world. They will be the first humans to have never been on Earth. The distinction is enormous. Home for them will be a rumour their robot nannies told them about. While the embryo ship waits for centuries to wake up, engineers on Earth keep watching the calendar. Because a strange question has started to haunt every interstellar planner's desk. If we launch today, will we even be the first ones to arrive? In 2006, an engineer named Andrew Kennedy published a paper with a title that sounded almost silly. It was called Interstellar Travel: The Weight Calculation and the Incentive Trap. The math inside it, however, was the coldest joke ever played on the interstellar dream. Kennedy asked a simple question. If you launch a starship today, using the best propulsion humanity can currently build, how long will it take to reach Alpha Centauri? The honest answer is somewhere around 1,000 years, give or take, depending on your design. Now, he said, consider the rate at which human propulsion technology is improving. Rocket performance has roughly doubled every few decades throughout the modern era. Engines get more efficient, materials get lighter, mission designs get cleverer. If that trend continues even slowly, then a ship launched 100 years from now will be significantly faster than a ship launched today. Here is the twist. If you launch now at low speed and someone else launches a century later at higher speed, that later ship will catch up and pass you in mid-flight. Your crew, still cruising, will watch a newer vessel streak past them, wave, and arrive at the destination years or decades before you do. All your effort, all your sacrifice, all your generations of passengers wasted. The second ship got there first. Kennedy ran the numbers for different rates of technological improvement. The results were brutal. For any realistic growth rate in propulsion performance, the optimal time to launch an interstellar mission is almost never now. It is always better to wait. A few decades of engineering progress on Earth outpaces decades of travel across space. The effect has a name now. Mission planners call it the weight calculation, or the incentive trap. It is the reason serious interstellar planners sometimes argue that launching a crewed starship today would be a kind of noble suicide. You are guaranteed to be overtaken. Your arrival, when it finally happens, will be at a colony that was founded decades earlier by a faster ship that left after you. The math changes only if technology growth stops. If humanity freezes its propulsion capabilities at their current level and makes no further progress, then launching today is worth it because no faster ship is ever coming. But every engineer who has ever worked on this problem assumes progress will continue, which means, in a cruel feedback loop, the best reason to launch is the one scenario that makes the launch look saddest. There is one escape from the trap. If the destination is time-sensitive, for example, if Earth itself is in imminent danger and a crewed backup must be established immediately regardless of arrival order, then the weight calculation loses its force. A lifeboat does not care about being overtaken, it just has to leave. Some theorists have suggested this is precisely why no interstellar mission has been attempted yet, not because it is impossible, but because rational planners keep running the weight calculation and concluding every decade that the right year to launch is 20 more years from now, and 20 years later the calculation reruns with the same answer. The first crew to actually leave, under current incentives, will almost certainly be desperate. They will launch knowing faster ships may follow, and once they leave, their world will shrink to the inside of the hull, where silence becomes the dominant sound in their lives. 20 years into the voyage, the chief medical officer sits in the observation bay and writes the same entry in her log that she's written for 300 days in a row. No new contacts, no new signals, crew stable. The ship is deep in the interstellar medium now, a region so empty that passing through it is almost harder than it sounds. There are no stars close enough to show a disk. The target system ahead is still a pinpoint. The home star behind is a brighter pinpoint. Everything else is a black canvas sprinkled with fixed dots of light that have not shifted noticeably for a decade. This is the middle of the mission, the part no one trained for, because no one has ever experienced it. Every human explorer in history had something to look at. Magellan had coastlines, Shackleton had ice, the Apollo astronauts had the Earth looming outside their windows, blue and alive. Even the crew of the International Space Station on their longest tours can look down and see the planet rolling beneath them. They can see their home. The interstellar crew looks out and sees the same view they saw 10 years ago. And they will see that same view for another 10 or 20 or 50 years. The stars do not move across the sky at human timescales. The ship is crossing distances so vast that even at near light speed, the visual universe appears almost frozen. The destination grows brighter by a fraction of a degree per year. The origin dims by the same. Mission planners call this the long middle. Simulations of it have been run on Earth, in Antarctic research stations and in isolation experiments like Mars 500, where crews were sealed in mock spacecraft for over 500 days. The results are consistent. Human beings handle the first few months of isolation remarkably well. Adrenaline and novelty carry them through. Around month 6, morale begins a slow decline. Around month 12, minor interpersonal conflicts become major. Around month 18, crews report a symptom that psychologists have named long eye, where the individual stares at fixed points for hours without being able to account for the time. Now extend that to a 20-year cruise, or a 50-year cruise, or a 200-year generation ship. No experiment has ever run that long. The longest controlled isolation study in history is under 2 years. Everything beyond that is extrapolation. The most honest answer human psychology can give about a multi-decade interstellar mission is, we do not know what happens. We have never kept a human being in that state long enough to find out. There are clues, though, and most of them are grim. The crew of a Soviet-era Antarctic research station in the 1980s experienced what was later called winter over syndrome. Symptoms included memory loss, difficulty concentrating, emotional flatness, and in severe cases, hallucinations. One crew member murdered another over a game of chess. Another tried to burn down the station. All of this after only one winter of isolation, with live radio contact to home, knowing a supply plane would arrive in spring. The interstellar crew has no supply plane. Their radio signal to Earth takes years to cross the gap. Their chess game, if it goes wrong, has no outside referee. And then there is the thing the long middle hides. Every cubic mile of vacuum is peppered with debris, most of it too small to see, all of it moving relative to the ship at velocities that turn dust into artillery. The ship is not drifting through empty space. It is driving through a minefield, and the mines are the size of sand grains. The ship's radiation monitor, mounted on the forward bulkhead, ticks quietly every few seconds, even inside the thickest part of the vessel. It has never gone silent. Not once in 20 years. Space radiation is the quietest killer on any interstellar mission. It does not announce itself. It does not cause the ship to shake or the alarms to scream. It simply passes through the hull, through the shielding, through the crew quarters, and through the human bodies inside, leaving microscopic damage at every point of contact. The crew does not feel it. They just age, statistically, a little faster. Their DNA acquires tiny errors. Their chance of cancer climbs. On Earth, the atmosphere and the planet's magnetic field deflect almost all of this radiation. At the International Space Station's altitude, crews receive roughly 100 times more radiation than people on the ground. A 6-month tour gives an astronaut about the lifetime radiation dose of a typical nuclear plant worker. On a trip to Mars, one of the biggest medical unknowns is whether the crew will arrive healthy enough to perform their mission. Interstellar space is much worse. Outside the protective bubble of the home star's magnetic field, known as the heliopause, the dominant radiation source is galactic cosmic rays. These are not the gentle particles of solar wind. They are atomic nuclei, mostly hydrogen and helium, accelerated by distant supernovas to near the speed of light. A single cosmic ray particle carries the kinetic energy of a thrown baseball, concentrated into something smaller than an atom. When one of them hits a human body, it does not just deposit energy at the point of impact. It creates a cascade of secondary particles, like a single bullet striking a stack of glass panes, sending fragments through every pane behind it. A single cosmic ray track through a human brain can damage thousands of neurons along its path. NASA studies from the 2010s showed that mice exposed to simulated cosmic ray doses developed permanent cognitive impairment. Their ability to navigate mazes, remember objects, and form new memories was measurably degraded. Now, the shielding math. To block cosmic rays, you need mass, lots of it. Physicists estimate that a fully protected interstellar crew would need about 6 feet of water shielding, or an equivalent mass of rock or metal surrounding the entire habitat. That is a shell weighing thousands of tons. Every ounce of it has to be accelerated to a fraction of the speed of light, then decelerated at the destination. The rocket equation does not forgive shielding, it punishes it. And even 6 feet of water only reduces the dose by a factor of a few. It does not eliminate cosmic rays. Nothing reasonable does. The highest energy particles punch through almost anything humans can reasonably carry into space. You can reduce exposure, you cannot stop it. Over a 20-year interstellar cruise, even with maximum shielding, the crew accumulates a radiation dose roughly equivalent to several hundred chest X-rays per day, every day, for the length of the mission. Studies suggest cancer risk from such exposure climbs above 50%. Cognitive decline becomes likely, not possible. The real horror of cosmic radiation is that it is steady. There is no storm to ride out, no shelter to run to. The ship is marinating in it from launch to landing. And then there is the fast radiation, the rare, sudden kind. Because when the ship is moving at a fraction of the speed of light, even a single grain of sand hits with the force of a small bomb. At 3 in the morning, ship time, a single atom of hydrogen drifting peacefully in the dark is suddenly struck by a starship moving at 20% the speed of light. The atom and the ship's hull trade places in energy terms. A burst of X-rays flashes. A microscopic crater appears in the forward shield. The impact register logs another hit. There are roughly 10,000 such hits per second. This is the reality no glossy starship illustration shows. The front of an interstellar vessel in flight is being bombarded continuously by the thinnest possible enemy. Stray hydrogen atoms, dust grains, the occasional piece of interstellar debris larger than a sand grain. At Earth orbit speeds, these particles are harmless. A dust grain floating at a few miles per second is not much of a threat. A spacecraft hull can usually ignore it. At relativistic speeds, the math flips into nightmare territory. Kinetic energy scales with velocity squared. Double the speed, quadruple the impact energy. Go 10 times faster, the impact is 100 times more violent. Go 1,000 times faster, 1,000,000 times more violent. At 20% the speed of the light, a dust grain weighing 1,000th of a gram strikes with the energy of a small artillery shell. A pebble strikes like a car bomb. A pea-sized rock would likely vaporize a significant portion of the ship. Mission engineers have spent decades trying to design shields capable of absorbing these impacts. The usual approach is called a Whipple shield, originally designed in the 1940s by astronomer Fred Whipple to protect spacecraft from micrometeoroids. It is a thin outer sheet separated by a gap from the main hull. An incoming particle strikes the outer sheet, vaporizes on impact, and the resulting cloud of debris spreads out before reaching the inner hull, where it can be absorbed more gradually. Whipple shields work beautifully at orbital speeds. At interstellar speeds, the incoming particles are moving so fast that the vaporization cloud itself still has enough kinetic energy to punch through the inner hull. This shield buys you a few microseconds. It does not stop the hit. Engineers at the Breakthrough Starshot project did a rough calculation in 2016. A chip-sized probe moving at 20% light speed would, over a 20-year cruise, be hit by about 10,000 impacts capable of destroying components. Most of the probes in the swarm would arrive at Alpha Centauri as shredded debris. Only a lucky fraction would make it through intact. That is for a spacecraft the size of a postage stamp. For a crewed vessel, the math becomes existential. A ship with a 1-mile frontal cross-section sweeps through many orders of magnitude more interstellar space than a Starshot chip. The probability of encountering a pebble-sized object during a multi-decade voyage is not small. It is near certain. The strategies engineers have floated range from magnetic deflection shields, which try to ionize and steer incoming particles away from the ship, to active laser systems that attempt to vaporize larger debris before impact, to simply accepting a statistical loss rate and sending multiple ships in formation on the assumption that at least some will arrive. None of these have been built. All of them add mass, complexity, and power requirements to a vessel that was already pushing the rocket equation past its limits. And all of them assume the crew survives the slow problems too, the ones that do not strike in an instant, the ones that hollow out the human mind itself. Month 170 of the voyage, the chief psychologist writes a short entry in his personal log. The crew is functional, but the word functional is beginning to lose its meaning. Every Earth-based space mission, no matter how long, has one feature in common with every other human expedition in history. The participants knew, at a visceral level, that someone was coming to get them. The International Space Station crew sees a supply capsule arrive every few weeks. Antarctic winter overteams know that spring will bring a plane. Submarine patrols end in months. Even soldiers in the most grueling military deployments know their tour has a date. The interstellar crew knows nothing of the kind. The mission is not a tour, it is the rest of their lives. The nearest human being outside the ship is light years away. The nearest breathable atmosphere is light years away. The nearest place where they could set foot on solid ground, in gravity without a suit, is light years away in either direction. Their entire world has shrunk to the volume of the hull, roughly a few million cubic feet, forever. Psychologists studying this scenario have borrowed a grim term from Antarctic research. They call it chronic residency, a state of mind that develops when a person's environment becomes fully and permanently defined by a sealed habitat. The outside world stops feeling real. Earth stops feeling real. The crew begins to treat the ship itself as the universe. At first, this is protective. The hull becomes home. The routines of daily life, meals, shifts, maintenance, become comforting. Crew members who are strangers at launch become, by year 5, the only family they will ever know. Then, slowly, the opposite effect kicks in. The hull starts to feel like a prison. The same faces, the same corridors, the same meals. Psychological researchers studying long-duration isolation have documented a phenomenon called solipsism syndrome, where individuals begin to doubt that anything outside their immediate environment exists at all. Earth becomes a memory they are no longer sure is real. Family members become characters in an old story. Even the stars outside the window lose their emotional weight. The symptoms accumulate. Sleep disorders within months, interpersonal conflict within a year, depression within 2. By year 5 in most isolation studies, at least one crew member has developed a severe mental health episode. By year 10, statistical models suggest the number climbs toward every crew member. And here is the thing that keeps mission planners honest. No one on Earth has ever tested this. The longest continuous human isolation experiment in history lasted 520 days. It was called Mars 500, run by Russia's Institute of Biomedical Problems. The crew came out physically intact. Psychologically, they all reported severe difficulty readjusting to normal life. 2 of them developed clinical insomnia that persisted for months after the mission ended. An interstellar voyage is 20 times longer, 30 times, 50. Simulations can only model what is understood, and the deep middle of a multi-decade Starship mission is not understood. It is a gap in human knowledge, and the first crew to experience it will also be the first to document it, on timescales so long that their reports will arrive years after the problem became terminal. The ship's air, water, and food systems are supposed to support them through all of it. If any one of those systems develops a leak, this psychological problem becomes the second worst thing happening on the ship. In a concrete bunker outside Tucson, Arizona, a facility called Biosphere, 2 sites mostly empty now, its huge glass domes reflecting the desert sky. In 1991, 8 volunteers sealed themselves inside it. The goal was simple: live off a closed ecosystem for 2 years, with no air, water, or food coming in from outside. The bunker would be their starship. 10 months in, the oxygen was gone. Not all of it, just enough to trigger altitude sickness at sea level. Crew members began gasping during minor tasks. Headaches became constant. Sleep became impossible. The scientists running the project eventually pumped oxygen in from outside to keep everyone alive. The experiment continued, but the crew spent the rest of the mission breathing imported air, which meant the closed loop had failed. The cause was a surprise to everyone. Microbes in the soil, introduced to support the crops, were consuming oxygen faster than the plants could produce it. The carbon dioxide they released then bonded with the unsealed concrete of the facility's interior walls, locking it away and breaking the expected cycle. A single unaccounted-for chemical reaction had nearly killed 8 people. Biosphere 2 is the most ambitious closed life support experiment ever attempted by humans. It ran for 2 years. It failed in the first year. Now imagine the same problem, but the facility is a starship and there is no outside. A crewed interstellar mission must recycle everything. Every breath of air the crew exhales must be scrubbed of carbon dioxide and replenished with oxygen. Every drop of urine and sweat must be purified back into drinking water. Every meal must come from food grown on board, fertilized by the crew's own waste, in soil or hydroponics that remain productive for decades. Every trace chemical, every microbe, every gas balance must stay within survivable limits for the entire voyage. No resupply ship is coming, no backup is available. The International Space Station, the best closed-loop system humanity has ever operated in space, recycles about 90% of its water and produces none of its food. The remaining 10%, plus all meals, is flown up from Earth every few weeks. If resupply stopped, the crew would survive for months, not years. A starship must hit 100% or close to it, and hold that number for decades. Mission studies have identified dozens of potential failure modes: a broken pump in the water recovery system, a bacterial infection in the algae tanks, a slow leak in the oxygen generator, a fungus in the wheat crop that sterilizes the next generation of seeds. Any single failure, if not caught in time, cascades through the rest of the system. The air goes bad. The water gets contaminated, the food stops growing. The crew has weeks, maybe days, to fix what broke before the habitat becomes unlivable. Engineers refer to this as the single-point failure problem. On a short mission, redundancy solves it. You carry 2 oxygen generators. If one fails, the other takes over until you return home. On an interstellar mission, redundancy has a harder ceiling. Every backup system is mass. Every ounce of mass is fuel, and even the best backup eventually wears out. Over a 50-year voyage, the odds of at least one critical system experiencing a catastrophic failure approach certainty. Mission planners do not ask whether the life support will break. They ask when, and whether the crew can fix it in time. And the crew itself, fighting those leaks, is doing so with bodies that evolution never designed for this kind of life at all. An astronaut returning from 6 months on the International Space Station cannot walk without assistance. Her leg muscles have shrunk by about 20%. Her bones have lost roughly 1% of their mass per month. Her heart, no longer pumping against gravity, has weakened. Her balance system, deprived of gravitational reference for half a year, is so confused that for days after landing she cannot sit up without feeling like the world is tumbling. This is after 6 months, in low Earth orbit. With a rigorous exercise program built into every single day of the mission, using specialized equipment that allows astronauts to run, row, and lift weights against resistance bands in zero gravity. Now stretch that mission to 50 years. The human body evolved under one constant condition: the gravity of the planet where it was built. Every organ, every tissue, every cell line assumes a steady downward pull of roughly 32 feet per second squared. Remove that pull, and biology starts to unravel in predictable ways. Bones lose calcium continuously because they are no longer being loaded. Muscles atrophy because they are no longer resisting anything. The cardiovascular system weakens because the heart no longer fights against the pooling of blood in the legs. bodily fluids shift upward into the head, causing the familiar puffy-faced look of astronauts in orbit. Over months, that fluid shift damages vision. More than half of long-duration station crew members have reported permanent changes to their eyesight after a single mission. Engineers know the fix: build a rotating habitat, spin the ship, or at least the crew compartment, to simulate gravity through centrifugal force. A large enough cylinder, rotating at the right rate, can produce an artificial version of Earth normal gravity at its outer wall. Generation ship concepts like Project Hyperion are designed around exactly this principle. The catch is size. A habitat that spins too fast produces a dizzying gradient where the crew's head and feet experience noticeably different gravity, and the Coriolis effect makes every head movement feel like a dropped elevator. To avoid these effects, the habitat must be enormous. Minimum useful diameters are measured in hundreds of feet, or better, thousands. Such habitats are not impossible to build, they are just very, very heavy, which brings the rocket equation back into the conversation, even meaner than before. There is also a darker problem. No one knows if human pregnancy, birth and child development work in artificial gravity. Zero studies exist. No mammal has ever been born and raised to adulthood in space. Experiments on mice in orbit have shown serious developmental problems. Their inner ear systems fail to form correctly. Their bone density never develops properly. If a generation ship relies on children being born in flight, the first generation might arrive at the destination physically incapable of walking on a planet's surface. And when the ship finally decelerates at the target star, the crew must step out, in pressure suits, into an unfamiliar gravity. Their bones, weakened by years of flight or centuries of artificial spin, may snap under their own weight. Their hearts, trained by rotating habitats to a slightly different rhythm, may struggle in real planetary conditions. The mission could succeed perfectly in every engineering sense, and still deliver a crew too broken to survive arrival. And that is before accounting for what cosmic radiation does to the brain, which turns out to be worse than anyone imagined. A neuroscientist named Charles Limoli, working at the University of California, Irvine, ran an experiment in 2015 that should have made headlines around the world. He exposed lab mice to doses of simulated galactic cosmic radiation, equivalent to what a crew would receive on a trip to Mars. Then he tested the mice on learning and memory tasks. The results were grim. Even months after exposure, the mice showed persistent cognitive impairment. They could not remember objects they had seen before. They became anxious. Their ability to learn new tasks dropped sharply. When Limoli's team examined the mice's brains under a microscope, they found the reason. The cosmic ray particles had literally carved channels through the brain tissue, destroying neurons and disrupting the connections between them. Each high-energy particle acts like a microscopic bullet. It passes through the skull, through the brain, and out the other side. Along its path, it damages or kills every cell it touches. A single cosmic ray can affect thousands of neurons in a single track. The human brain has billions of neurons, so one particle does not cause obvious trouble. But cosmic rays hit the brain thousands of times per day, every day for years on end. The damage accumulates, slowly, silently, without any dramatic symptoms until a threshold is crossed. On a 6-month Mars mission, follow-up studies have estimated that crew members might experience measurable cognitive decline. Reaction times slow, short-term memory weakens, decision-making becomes less reliable. The astronauts would not become stupid. They would become slightly worse versions of themselves, in ways subtle enough that they might not notice the change at first. On a multi-decade interstellar mission, the math becomes existential. A 50-year voyage exposes the crew to radiation doses 50 to 100 times higher than a Mars mission. If Limmerle's findings scale linearly, which is the conservative assumption most researchers use, then by the halfway point of an interstellar cruise, the crew's cognitive performance may have dropped by a significant fraction. They would still be functional. They could still operate the ship, but they would be operating it with brains that had been shot through by millions of microscopic particles for decades. The critical jobs on a starship require sustained mental sharpness, navigation, system diagnostics, emergency response. Any of these can be the difference between life and death in a single bad hour. A crew whose average cognitive ability has been degraded by 20 or 30% is not a minor problem. It is a crew that may make a critical error during the exact moment when error is most expensive. Shielding helps, but as established earlier, complete shielding is mass prohibitive, and partial shielding only reduces the dose. Dietary countermeasures like antioxidant supplementation have shown modest protective effects in animal studies. None of them stop the damage, they slow it. Here is the cruelest implication. The crew that arrives at the target star system may not be the same crew mentally that launched. Their personalities may have shifted, their memories of Earth may have grown hazy, their ability to carry out the mission they trained for may have eroded without them realizing it. They might step out onto an alien shore and no longer fully remember why they came. And when they finally try to send a report home about what they found, they will discover the other curse of interstellar distance. Communication has become almost meaningless. The ship's communications officer has a job that most engineers would call the loneliest profession ever invented. Every morning she sits at her console and composes the day's transmission to Earth. It is a 1,000-page document of telemetry, science data, health logs, and personal messages from the crew. She compresses it, encodes it, and fires it at the receding dot of the home star using a tight beam laser communication system. The beam leaves the ship at the speed of light. It crosses space for the next 4.5 years. Then it arrives at a receiving array on Earth, where it is decoded and read by the descendants of the mission planners who originally launched the ship. The crew member who sent the message is either still alive and much older or dead. By the time Earth composes a reply and sends it back, another 4.5 years will pass. The crew receives the answer 9 years after their original question. In total, a single round-trip conversation with home takes roughly a decade. This is the situation when the ship is at Alpha Centauri, the closest possible interstellar destination. Farther targets make it worse. A mission to Tau Ceti, about 12 light-years away, means 24 year-round trips. A mission to the centre of the galaxy is purely theoretical. The ship and the planet Earth become, for practical communication purposes, two different civilizations that can only exchange postcards across generations. Mission planners have tried to work around this gap in several ways. Pre-recorded databases allow the crew to access Earth's accumulated knowledge up to the moment of launch. Libraries of entertainment, educational material and cultural records are stored on the ship's computer. But these are frozen in time. The moment the ship leaves, Earth continues to evolve. New music is written, new scientific discoveries are made, new languages emerge. The crew's cultural connection to home stops at launch and slowly drifts further out of sync with reality on the planet. Some studies have proposed what is sometimes called a synchronous contact. Earth would broadcast a continuous stream of updates on everything happening back home. The crew would receive this stream years later, watching current events as ancient history. They would know, intellectually, what their home planet is doing right now, but they could not ask questions. They could not participate. They could only observe on a delay a world that had moved on without them. There is also a much darker scenario. What happens if Earth stops transmitting? A geopolitical collapse, a global war, a technological regression, a simple loss of interest in a mission that happened 2 centuries ago. Any of these could cause the home signal to go silent. The crew, deep in interstellar space, would notice gradually. First a missed transmission, then another, then months of static, then silence. They would have no way to know what happened. They would not be able to ask. They would have to continue the mission alone, not knowing whether Earth was quiet because humanity had moved on or because humanity was gone. Mission planners have a nickname for this scenario. They call it the broadcast blackout, and the strangest feature of it is that no crew could ever verify, in real time, whether Earth still exists at all. While they wait for words from home, their own shipboard culture begins to separate from Earth's culture in ways no one on either end can predict. In linguistics departments around the world, researchers have documented a curious pattern. Whenever a group of speakers becomes isolated from the main body of their language, their speech starts drifting. Not randomly, in predictable ways. Vowels shift, grammar simplifies or reorganizes, new words are coined, old words fall out of use. Within a few generations, the isolated dialect can become mutually unintelligible with the parent language. This happens on Earth in a few centuries, across communities separated by oceans or mountain ranges. On a starship, separated from Earth by light years and decades of one-way radio contact, the effect runs at high speed. Linguists studying hypothetical generation ship scenarios have modelled the language drift. On a ship carrying a few hundred people in permanent isolation, the first generation speaks roughly the same dialects as the launch-era Earth. The second generation, born on the ship and raised only by their parents, begins to develop distinctive speech patterns. By the 5th generation, many of the original Earth idioms have been replaced by shipboard equivalents that would sound foreign to someone back home. By the 10th generation, the language on board is a new dialect, possibly a new language entirely, with its own grammar and vocabulary. Meanwhile, on Earth, the original language has also changed. Slang has evolved. New technologies have created new terminology. Political and cultural shifts have altered the meanings of common words. The language the ship received in its computer banks at launch is, 2 centuries later, a historical artifact on Earth. When the ship finally arrives at its destination and beams a report home, the crew's message is composed in a dialect that no Earth speaker fully understands. Earth's reply, composed in modern terrestrial language, is equally foreign to the crew. Both sides need linguistic translators to pass each other's transmissions. The drift does not stop at language. Cultural evolution happens in parallel. The crew's religious practices, if any, diverge from Earth's. Their holidays, inherited from launch-era traditions, transform into new observances specific to shipboard life. Their art reflects the enclosed, artificial world of the vessel, rather than the open landscapes of Earth. Their food, grown in onboard hydroponic farms, evolves away from Earth cuisine toward whatever the ship's ecosystem can sustainably produce. By the time a multi-generational starship reaches its target, its crew represents a separate branch of humanity. They speak a different language, they eat different food, they worship different ideas, if they worship at all. They look at the stars through the ship's windows and see them in a different emotional register than their earthbound counterparts, because for them the stars have always been the ceiling of home, not a distant and inaccessible realm. This has a consequence no one on Earth can fully predict. When the ship lands and the crew disembarks into a new world, they are, in a real sense, not human representatives of Earth anymore. They are a sister species sent out centuries earlier, now carrying their own distinct culture. A diplomatic meeting between Earth and the colony, once communication is re-established, would resemble contact between two related but separate civilizations. And then the next problem surfaces, because by the time the crew finishes their voyage, the agency that launched them may not exist at all. The political entity they report to may have collapsed, merged, or transformed into something they would not recognize. Their bosses are gone, their funding is gone, their entire institutional home has vanished into history. The longest-running space agency in human history is NASA, founded in 1958. It is younger than the oldest commercial airlines, younger than the United Nations, younger than most of the political institutions that shape the world today. In the grand timescale of interstellar travel, it is brand new, and there is no serious reason to believe it will still exist in its current form 2 centuries from now. Consider the record of large human institutions across time. The Roman Empire lasted about 500 years in the West. The British East India Company, one of the most powerful corporations ever created, lasted 274 years. The Soviet Union lasted 69 years. The average lifespan of a major multinational corporation in the modern era is under 50 years. Governments rise and fall on even faster timescales. Borders move, flags change, languages of power shift from Latin to French to English to whatever comes next. Now consider a starship launched by an agency, a coalition, or even a company. That organization funds the mission, manages communications, receives the science data, and presumably coordinates the eventual follow-up missions or colony support. The mission's entire relationship with home is mediated through this institution. What happens when the institution dies? Halfway through a multi-decade voyage, the ship beams a routine transmission to its control center. No response. Months later, still no response. The crew eventually learns from fragmentary radio chatter from other sources on Earth that the agency has been dissolved. Its funding was cut. Its mission was declared obsolete. A new government, or no government, has taken over. The ship's flight controllers retired and passed away. The organizational knowledge of how to receive and process the mission's data has been lost. The crew is still flying, their ship is still operational, their mission is still valid in a scientific sense, but no one on Earth is listening anymore. Historians of space exploration sometimes point out that this has already happened on small scales. Several of the Soviet-era space probes sent to Venus and Mars returned data that was never fully analysed because the scientific teams that understood the instruments had dispersed. Some of NASA's early Pioneer and Voyager data required decades of work to fully interpret, because the original engineers had retired. The institutional memory of a space mission is fragile. On a 2-century interstellar voyage, it can evaporate entirely. Some mission concepts try to plan for this. A heritage package might include the full technical documentation of the mission, stored in multiple locations on Earth and on the ship, in formats designed to survive long institutional gaps. Contingency plans might involve handing off the mission to successor agencies, or posting the science data as an open public resource that future generations can access even if no formal agency remains. None of these solve the core problem. The crew is flying a mission for an employer that no longer exists. They are reporting to a command structure that has been replaced. They are the last living representatives of a project that is, on Earth, ancient history. When they eventually arrive at their destination, the welcome home broadcast they imagine receiving may never come. The Earth that launched them is gone. The Earth that exists now has never heard of them. And the planet they arrive at might not offer a welcome either, because exoplanets seen from a distance lie. For 3 years during the deceleration phase, the crew watches the target planet grow from a pixel to a disk. The ship's telescopes have been studying it in increasing detail. Oxygen lines in the atmosphere, water vapor in certain bands, a magnetic field detected from its interaction with the parent star. All the signatures that, 50 years ago, made Earth-based astronomers circle this planet as the most promising destination in the known sky. The ship enters orbit. The first high-resolution images come back. The crew stares at the screen in silence. The planet is a corpse. The oceans they expected are frozen. The continents are scoured bare. The atmosphere, on closer inspection, is mostly carbon dioxide with traces of oxygen that turn out to be produced by a minor chemical process, not by life. The magnetic field is weaker than predicted, too weak to protect a surface ecosystem from stellar radiation. The parent star, viewed up close, is more active than Earth-based observation suggested. It flares frequently, sterilizing the surface of anything nearby. The planet looked Earth-like from 40 trillion miles away. It was a lie of distance. This is the scenario that keeps exoplanet researchers awake at night. Astronomers can detect certain features of distant planets: size, approximate mass, rough atmospheric composition, surface temperature within wide error bars. Everything else is inferred, and the inferences are often wrong. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets by watching them cross in front of their parent stars. Many of these worlds were flagged as potentially habitable. Later, more detailed studies of a few of these planets, using telescopes with better spectroscopic capabilities, revealed problems. Some had atmospheres so thick they would crush a human. Others had surface temperatures that made the initial estimates look wildly off. Some were tidally locked, one side always facing their star, the other side in permanent frozen darkness. The kinds of observations needed to say, with real confidence, whether a given exoplanet is habitable are still largely beyond current technology. Confirmation requires direct imaging, high-resolution spectroscopy of the atmosphere, mapping of surface features, detection of biosignatures that cannot be faked by non-living processes. Building a telescope capable of all that, for a planet decades of light years away, is a multi-generational engineering project in its own right. Mission planners know this. Every serious interstellar proposal includes language about arriving at a candidate planet, with the understanding that the crew may find on arrival that the candidate is uninhabitable. This is the worst possible outcome after a successful voyage. The ship has worked, the fuel has held, the crew has survived, and the destination is a grave. The options at that point are brutal. Spend the remaining life of the ship in orbit, waiting for a rescue that will not come, attempt to land anyway, in pressure suits, and survive inside the ship while the crew's food supplies dwindle. Try to reach a secondary candidate in the same star system, if one exists, burning the remaining fuel reserves, or accept that the mission has failed and live out the rest of the crew's lives in orbit around a dead world. None of these options include the word home. because the fuel to return to Earth was never on board in the first place. And even if the world were alive, the engineering of making it livable for humans would take longer than any one crew's lifetime to complete. Picture a planet that is close to habitable, but not quite. Its atmosphere is thin, its average temperature is below freezing. There is water, but it is mostly locked in subsurface ice. The surface is breathable only with the supplemental oxygen mask. The crew has arrived. The decision before them is whether to try to terraform the world into something their descendants can walk on barefoot. The idea of terraforming, engineering a planet's environment to support human life, sounds like a solution to the dead world problem. A crew that cannot return home could, in theory, transform its destination into a new home. The timelines are what stop this idea in its tracks. Mars is the most studied terraforming candidate in human history. It is next door, relatively well mapped, and climate models of its transformation have been refined for decades. The consensus estimate among engineers and planetary scientists who take the question seriously is that fully terraforming Mars would require between 1,000 and 100,000 years. Some studies go higher. The wide range reflects the number of unknowns, not optimism. Even the fastest scenarios involve enormous engineering projects. Factories covering thousands of square miles, producing greenhouse gases to warm the atmosphere. Deliberate impacts of water-rich asteroids to deliver hydrogen to the surface. Planetary-scale mirrors in orbit to increase the amount of stellar energy reaching the ground. Genetically engineered microbes released by the ton to produce oxygen over centuries. Every one of these projects requires industrial infrastructure that itself must be built from local resources by a population starting from nothing. On Mars, the starting population would be at best a few thousand humans with a manufacturing base the size of a small town. On an exoplanet, the starting population would be a single Starship crew, possibly a few hundred people, far from Earth, with no resupply. The industrial capacity required to terraform a world is orders of magnitude larger than any Starship can carry. Even assuming the crew survives long enough to begin, even assuming they successfully build the first generation of terraforming infrastructure, the timeline to a breathable atmosphere is still measured in centuries, not years, not decades, centuries. This means the crew that arrives will never walk on the surface in regular clothes. Their grandchildren, possibly, might. Their great-grandchildren might see the first thin forest take root. Their descendants, many generations on, might eventually inherit a planet that resembles Earth in climate. The first arrivals are functionally a work crew. Their entire lives are spent laying the foundations of a transformation they will never witness. They live in pressurized shelters. They eat food grown in domes. They die before the atmosphere outside their windows becomes breathable. There is a kinder alternative. The crew could settle permanently inside enclosed habitats without trying to change the planet. Domes, underground cities, pressurized structures, powered by local resources. This works if those resources are available, which is a separate and difficult question. But even in the best case, the crew is living indoors, permanently, on a world whose outside is lethal. Either option ends the dream of stepping out of the ship and breathing alien air. The dream was never realistic on any timeline the crew would live through, and the last dream, the one mission planners have most quietly abandoned, is the idea that the ship itself might ever turn around and bring the survivors back. Somewhere in the archive of every serious interstellar mission study, there is a paragraph about return propellant. It is usually short, it is always honest. It says, in effect, that no plan exists to refuel the spacecraft at the destination. Every rocket that has ever returned to Earth from another world did so because its return fuel was either carried from home or was simple enough to be manufactured at the destination with minimal infrastructure. Apollo astronauts carried their return fuel from Earth, stored in the lunar module's ascent stage. Mars sample return missions, still in the planning phase, rely on carrying the return fuel with them, or on small local propellant factories using Martian atmosphere as feedstock. In both cases, the fuel is chemical, rough, easy to handle, easy to make if the raw materials are available. Interstellar return is a different beast entirely. To leave Proxima Centauri and return to Earth at any reasonable speed, the ship needs to accelerate to a fraction of the speed of light again, which means a new fuel tank comparable in size to the original launch, which means, depending on the propulsion technology, either tens of thousands of tons of fusion fuel or tons of antimatter, or some other exotic substance that is not lying around the surface of a foreign planet. Consider fusion fuel. Helium-3, the fuel proposed for Project Daedalus, is present in trace amounts in the atmospheres of gas giants. If the target star system has a gas giant, and if the colony has survived long enough to build a helium-3 mining operation, then, decades later, enough fuel might eventually be harvested for a return mission. The mining infrastructure required is vast. The refining process is complex. The timeline is generational. Consider antimatter. It does not exist naturally in usable quantities anywhere, including at the destination. To produce antimatter, the colony would need to build particle accelerators of the kind that currently exist on Earth only at places like CERN. Those accelerators require power plants, precision manufacturing, high-energy physics expertise and raw materials. A Starship crew, beginning from scratch on an alien world, is not going to produce antimatter within any timeline that matters. Consider in situ manufacture of conventional chemical fuel. This is theoretically possible if the target world has the right materials. It is also useless, because chemical fuel cannot provide interstellar velocities. You could make enough to get the crew to orbit around the target planet, which they presumably already are. You cannot make enough to cross 40 trillion miles. Engineers have run the calculation in multiple ways. Every path to a return mission requires infrastructure at the destination that is larger than the Starship itself. The arrival crew would have to build that infrastructure. Building it takes time, measured in generations during which the original crew ages and dies. The eventual return ship, if it ever flies, would carry their descendants back to an Earth that none of them have ever seen. Some mission studies have proposed a simpler alternative: send the return fuel ahead of the crew in a robotic mission launched decades earlier. The fuel waits in orbit around the target planet. The crew arrives. The fuel is there. They decelerate, refuel, and eventually return. The problem is the same rocket equation that caused all the trouble in the first place. Sending the fuel ahead requires its own propulsion system, its own mission, and its own enormous fuel reserves. It is a second interstellar mission, with all the same difficulties flying ahead of the first. And the idea that an alien world will cooperate by providing the raw materials for a return journey is, to put it gently, optimistic. On a whiteboard at NASA's Johnson Space Center, someone has drawn a smiling stick figure next to a Martian rock. A speech bubble above the stick figure says, "Just make fuel from this." Underneath, in smaller handwriting, another scientist has written, "Yes, but." The concept of in situ resource utilization, sometimes just called ISRU in the trade, has been NASA's answer to many impossible logistics problems for decades. The idea is elegant. Do not carry everything from Earth. Use the raw materials available at your destination. make water from polar ice, make oxygen from atmospheric carbon dioxide, make rocket fuel from hydrogen and carbon compounds found on the surface, build structures from local regolith. For Mars, this approach has been studied in extraordinary detail. The Perseverance rover, which landed in 2021, carried a small experimental device called MOXIE, short for Mars Oxygen In Situ Resource Utilization Experiment. It successfully produced small amounts of oxygen from Martian atmosphere. It was a historic first. It also produced roughly enough oxygen in a single session to fill a small balloon. Scaling that device up to produce breathing air for a human crew, let alone rocket fuel for a return mission, would require an industrial facility that Mars settlers have not yet built, because they are not there yet. Now extend the same concept to an exoplanet that has never been visited by any probe, that lies 40 trillion miles from Earth, whose composition has only been inferred from spectroscopic measurements of its parent star. The crew arrives with a general idea of the planet's chemistry. The surface probably contains certain metals. The atmosphere probably contains certain gases. The oceans, if any, probably have certain salinities. All of this is best guess data from telescopic observations taken decades earlier. What the crew does not know, until they land, is the specifics. Which isotopes are present in what proportions? Which minerals are available in miniable concentrations? Which microbial or chemical processes are active in the soil, and whether any of them are toxic to the equipment or the crew? Whether the ice they expected to find is actually water ice, or something else entirely like methane or ammonia, which would require different extraction techniques. Every one of these questions matters for in situ resource utilization. A mining process designed for one chemistry fails on a different chemistry. A fuel synthesis plant optimized for Earth-like oxygen ratios fails when the atmosphere contains unexpected levels of sulfur or nitrogen compounds. The crew's entire industrial strategy may have been designed for a planet that turns out, on close inspection, to be different from what they planned for. Alien chemistry is not a minor engineering adjustment. It is a potential mission killer, and diagnosing it requires time, months of careful surveys, years possibly, before a viable industrial base can be established. Meanwhile, the crew is consuming the supplies they brought from Earth. Food stocks run low, spare parts dwindle. The life support systems designed for a finite mission duration begin to wear out. Every day spent setting up local resource extraction is a day drawn from a limited reserve, and when eventually a working in situ facility is built, the scale is usually small, a few tons of fuel per year, a few dozen gallons of water per day, enough to sustain a small colony, not nearly enough on any reasonable timeline to fuel a return mission to Earth. The crew is stuck. And on Earth, meanwhile, time is kept moving without them in ways they cannot easily imagine. Imagine, against all odds, that a returning starship somehow beats every obstacle and comes home. The fuel was found, the ship survived. The crew made it through. After a voyage measured in Earth time of maybe 2 centuries, they ease back into the solar system, decelerate through Jupiter's orbit, and transmit a greeting on the frequencies they remember using at launch. On Earth, nobody is listening on those frequencies anymore. 200 years of radio evolution, 200 years of political change, 200 years of technology churn. The protocols the crew knows are as ancient as Morse code would be to a modern engineer. Their transmission is not received as a welcome. It is detected, if it is detected at all, as a strange anomalous signal from deep space, a curiosity for some graduate student to investigate. When the ship is eventually identified, the reunion is strange. The crew steps off their vessel at whatever passes for a spaceport in the new era. The people meeting them are descendants, many generations removed, of the engineers who launched the mission. None of them ever met anyone on the crew personally. The photos in the welcome brochure are black and white. The language spoken is recognizable but dated. The crew feels like tourists in their own country. Their children and grandchildren, the ones they said goodbye to at launch, are long dead. Their great-grandchildren are also dead. The descendants alive today have only heard of them as historical footnotes. Our ancestor was one of the original crew of that mission. It is a story in a family tree, not a living relationship. The social dislocation is almost total. The crew's professional skills are outdated. Their political affiliations refer to governments that no longer exist. Their cultural references are ancient. They are, in the most literal sense, refugees from the past. They arrive in a future they are not prepared for, carrying memories of a world that no longer exists. Historians sometimes compare this to the experience of Japanese soldiers found in the jungles of the Philippines decades after World War II ended. Those men had been isolated for 30 or 40 years, still fighting a war that had ended generations earlier. When they were finally brought home, they could not adjust. Their families had grown old and died. Their country had become a completely different place. They were living ghosts. The interstellar crew would be in the same position, except by a factor of 10, or 20, or 50. Some mission concepts have tried to mitigate this. Video archives updated regularly from Earth, so the crew keeps some sense of how their home evolves. Cryogenic sleep, so the crew's subjective time aligns more closely with Earth time. Time-dilated near-light-speed missions, so the crew experiences only a few years of travel while Earth ages decades. Each of these buys something. None of them eliminate the problem. A crew that leaves Earth for the stars is for all practical purposes leaving their civilization. The civilization they return to, if they return at all, will be a different one. A stranger's country. A stranger's century. And if they were gone long enough, the strangest change of all may not be cultural or political. Earth itself, the physical planet, may have changed in ways no one expected. The returning crew looks out the window of their capsule as it descends through the atmosphere. The coastline below does not match their memory. The shape of the continents has drifted. The forests are a different colour. The river they remember flowing into a familiar bay now empties somewhere else, because the bay has silted in, or the river has been rerouted by human engineering. This is not a hallucination. This is Earth, 2 centuries after they left, doing what Earth always does. Continental drift moves the tectonic plates at roughly the speed a fingernail grows, about 1 inch per year. Over a 200-year interstellar mission, the continents move about 17 feet. On the scale of a planet, this is invisible. But the processes driven by that slow movement are not. Coastlines erode. Mountain ranges lift. Earthquakes and volcanic eruptions redraw the maps of entire regions. Climate change, even without human influence, shifts on longer timescales. Over the past 10,000 years, Earth has swung between warm periods and cool periods, glacial advances and retreats, changes in sea level of hundreds of feet. Over 2 centuries, these background changes are usually small. But when human influence is added, the pace accelerates. Since the Industrial Revolution began, roughly 2 centuries ago, global average temperatures have risen by about 2 degrees Fahrenheit, sea levels have risen by about 9 inches, and the atmosphere's carbon dioxide concentration has risen by almost 50%. If similar or larger changes occur in the next 2 centuries, during the crew's absence, Earth could look dramatically different on return. Coastal cities submerged, deserts expanded, forests migrated to new latitudes, species that used to thrive in one region gone or displaced. Biodiversity is the most fragile element. During the Holocene extinction event, which is still ongoing, species are disappearing at roughly 100 to 1,000 times the background rate that characterized pre-human Earth. Over 2 centuries, many of the animals and plants the crew remembers may no longer exist. The elephants, the polar bears, the coral reefs, the birds that sang outside their childhood windows. All of them could be gone by the time the ship returns, replaced by smaller, more generalist species that have adapted to the new conditions. The crew returns to a planet that is recognizably Earth, but also recognizably not the Earth they left. The weather patterns are different. The seasons arrive at different times, the crops grown in different regions, the wildlife strange. Add to this the human changes. New cities have risen, old cities have been abandoned, political borders have been redrawn, new religions have formed, languages have evolved, fashion, architecture, music, food, all have transformed. The ground the crew walks on, the air they breathe, the society they try to integrate into, is all new to them in ways they were not prepared to accept. Some mission planners have suggested that the most difficult adjustment would not be the technological change. Technology can be learned. The hardest change is the ecological one. The Earth of memory, with its specific forests and oceans and animals, is gone. What replaces it is a different planet wearing the same name, and against this backdrop a question lurks that mission planners have started to take more seriously: whether the returning ship should even announce itself at all. In 2008, a Chinese science fiction writer named Liu Qijin published the second book in a trilogy that would eventually win the Hugo Award. The book proposed an answer to Fermi's paradox, the question of why a universe so vast seems to contain so few detectable civilizations. The answer, called the dark forest theory, was chilling. The universe is a dark forest, and every civilization inside it is a hunter. To announce yourself is to invite destruction. The rational strategy is silence. Liu Qijin was writing fiction. But the theory has seeped into serious discussions among astrobiologists, SETI researchers, and interstellar mission planners, because it is not easy to dismiss. The basic logic runs like this. If intelligent life exists elsewhere in the galaxy, we have no way to know its intentions. If it is hostile, announcing our location is suicide. If it is benign, announcing our location costs nothing. The asymmetric risk, the logic argues, strongly favours silence. Humanity should not be broadcasting, it should be listening. Now apply this logic to a returning starship. The crew has been away for 2 centuries. They arrive at the edge of the solar system and prepare to announce their return to Earth. Standard procedure would be a full spectrum transmission, identifying themselves, their origin, and their mission. A beacon, in effect, that anyone within light years could detect. Before launching that beacon, the communications officer pauses, because she knows 2 things. First, Earth itself has been broadcasting for over a century already, through its own radio and television signals that leak into space. Second, nobody on Earth has ever verified that the galaxy is safe. If a hostile civilization is listening, any broadcast the crew makes adds to Earth's already existing radio signature. It provides triangulation data. It reveals the locations of both Earth and the returning ship. Some interstellar researchers have suggested that future missions should travel and communicate silently. Encrypted tight beam transmissions aimed only at known friendly receivers. No general announcements. No open beacon signals. A kind of interstellar stealth. Others argue the opposite. That stealth is impossible, because Earth has been radio bright for a century. That the galaxy, if it is dangerous, already knows we are here. That adding a returning ship to the broadcast mix changes nothing. The debate is unresolved, no consensus exists, and for a returning crew, this uncertainty is another cold weight to carry. The crew has survived the voyage. They have fuel to decelerate. They have functioning life support. They have Earth in their sights. And now, possibly, they face a question no previous explorer in human history has had to ask. Should they reveal themselves? A ship that stays silent may not find Earth. Without active communication, they may miss modern navigation beacons, miss safe arrival corridors, miss any instructions or updated protocols that would allow a safe landing. A ship that speaks may, in some small but non-zero probability, draw attention from something listening in the dark. There is no right answer. Mission planners, writing contingency documents, have sometimes left this section blank, with a note that future crews will have to decide based on information available at the time, and whatever the crew decides, they are, by every other measure, the survivors of a voyage no previous human has undertaken. In a sense, they are not just travellers. They are survivors from a century that no longer exists. A historian at a university campus decades in the future stands at a lectern and tells her students about a minor footnote in the history of space exploration. A small crewed mission was launched 2 centuries earlier, in an era when humans still believed interstellar travel might be possible within a generation. The mission was ambitious, even heroic. It was also, by modern standards, obviously misconceived. The historian mentions, almost as an aside, that the original crew of that mission is, in theory, still alive, aging on board a returning vessel somewhere in the outer solar system, due to arrive within the decade. A student raises her hand. Still alive? After 200 years? The historian explains time dilation. She explains how relativistic velocities cause clocks aboard the ship to tick slower than clocks on Earth. She explains that while 200 years have passed on Earth, only perhaps 50 years have passed on board from the crew's perspective. She explains that when they arrive, they will still be, biologically, people in their middle or late middle age. They will look like contemporaries of the historian's great-great-grandparents. They will, in every meaningful sense, be refugees from a lost century. This is a scenario interstellar researchers sometimes call the traveller's paradox. A crew can leave Earth, travel to a distant destination, and return, with their biological clocks having aged 50 years. Meanwhile, Earth's clock has aged far more. The crew arrives young relative to the society they left behind. Their children have been dead for decades. Their friends, co-workers, spouses are all gone. Only the crew itself persists, like a time capsule that has physically travelled the future and then opened itself on arrival. History offers rough analogies. Rip Van Winkle sleeping in a mountain cave and waking up to a world that has moved on. Crusaders returning from the Holy Land to find their estates confiscated and their wives remarried. Frontier settlers, cut off from civilization for decades, who eventually returned to cities that had grown unrecognizable. None of these analogies are quite right, because none of them involve the social isolation of a crew whose entire generational cohort has died without them. The Crusader could at least meet the sons and grandsons of people he remembered. The relativistic traveller skips so many generations that even those connections are lost. Psychologists have studied what happens when humans are reintegrated into societies that have changed dramatically during their absence. Refugees, political exiles, and long-term prisoners all experience a version of this. The common thread is grief. Not grief for a single lost person, grief for an entire lost world. The streets where they grew up, the songs they grew up with, the way people used to greet each other, all of it replaced by something unfamiliar. Some interstellar thinkers have proposed that relativistic crews might refuse to reintegrate at all. They might choose to stay together as a separate community, preserving their own time capsule culture even after landing. They might form small enclaves, old-fashioned by 2 centuries, existing at the margins of a society that barely understands them. This is the quiet tragedy of the interstellar crew. They went for the voyage, they survived the voyage, they came home, and home, as they knew it, did not survive the waiting. Their lives, their identities, the people they love, have been reshaped by physics, which leads to the deepest question of the entire mission. When home is gone, what does going home even mean? Somewhere in the philosophy department of a university, a professor writes on a chalkboard, "Home is a place you can return to. Can it be a time you can return to?" The question is not rhetorical. For an interstellar crew, the answer is probably no. Human identity is deeply tied to memory, place, and continuity. We are who we are because we remember being younger versions of ourselves in specific places with specific people. Our home is where those memories are anchored. A house, a neighborhood, a city, a country. When we return to those places, we touch the same stones we touched before, walk the same streets we walked before, and feel, briefly, a sense of continuity with our past selves. For a relativistic traveller, that continuity is broken in a unique way. The physical places still exist, sort of. The streets may have been repaved, the houses may have been demolished and rebuilt. The neighbourhoods may have been renamed or merged or transformed by waves of new residents. The city survives, but the city of memory is gone. More critically, the people are gone. Every person who knew the traveller as a younger version of themselves is dead. The childhood friends, the first teachers, the early mentors, the family members who shaped their earliest sense of self. All of them lived and died during the traveller's absence. This is a kind of identity problem with almost no precedent in human history. Most travellers, even long-absent ones, return to societies that contain at least some people who knew them. Their stories can be confirmed. Their place in the social fabric can be re-established. For the interstellar traveller, no such verification exists. The people who could have confirmed their memories are gone. Some philosophers have suggested that this makes the relativistic traveller a new kind of person. Not quite exile, not quite immigrant, not quite refugee. Something like a ghost, in the sense that ghosts are traditionally understood as spirits whose original time has passed, but who linger on in a later time. The traveller is biologically alive but historically displaced. Their era is over. They have outlived it. This has practical consequences. Legal systems assume continuous personhood. If a traveller left Earth 2 centuries ago, are they the same legal entity now as they were at launch? Their birth records exist. Their citizenship is theoretically valid. But the institutions that administered those records have changed. The country they were a citizen of may no longer exist in the same form. Their property, if they had any, has long since passed to descendants who are themselves long dead. Their bank accounts, if they were not cleverly structured, have been closed. The traveller may return to find that they own nothing, belong to no country, have no legal spouse or family, and exist in the modern world as a kind of administrative orphan. Special legislation may need to be passed to formally readmit them as citizens. the psychological problem is worse. Even with full legal reintegration, the traveller may not feel at home anywhere. The past is inaccessible, the present is foreign, the future is alien. They are a person out of time, dressed in the clothes of an era that no longer exists, speaking a dialect that has become archaic. Going to the stars is one choice. Never again belonging to any specific century is the consequence. And this brings the entire mission back to a single, brutal question. If no one who goes can truly come home, why does any mission planner still keep drawing these ships? In a conference room somewhere in the next century, a mission director is presenting a slide to a small committee. The slide shows the first ever crewed interstellar mission proposal, fully funded, fully engineered, ready to launch. Every calculation has been verified. Every system has been stress tested. Every ethical review has been passed. At the bottom of the slide is a single line. Return mission, not included. The committee already knows. They have read the briefing. They have studied the rocket equation. They have reviewed the volumes of analysis from the past century and a half. They understand, as thoroughly as humans can understand something, that the crew they are about to approve will never come back, and they will approve the mission anyway. Because the logic, cold as it is, pushes in that direction. Every civilization in the long timeline of Earth has, at some point, sent people on missions from which most of them did not return. The first humans to cross the Bering Land Bridge into North America. The first Polynesians to settle the islands of the Pacific, sailing into unmapped ocean with only what their canoes could carry. The first Europeans to board ships for the New World, knowing the odds of survival were uncertain and the odds of return even lower. The first colonists at Jamestown, the first settlers of the Australian outback. None of these were round trips. Most of the travellers died in the attempt or lived out their lives far from their birthplaces. Some of them arrived at destinations that killed them within months. Some built thriving communities. The historical pattern is clear. Humans have always accepted one-way voyages when the stakes were high enough. The stakes for interstellar travel are, in the long view, civilizational. A species confined to a single planet is vulnerable. Extinction events happen, asteroids strike, volcanic winters arrive, climates shift, diseases evolve. Entire biospheres have been reset multiple times in Earth's history. The modern environmental and political challenges facing humanity have, for many thinkers, made the case that Earth alone is not a safe long-term home for the species. Spreading humanity across multiple star systems is, by this logic, a kind of civilizational insurance policy. Even if every single interstellar mission is one way, even if every crew dies without returning, the net effect is that humanity exists in multiple places. If one place ends, others continue. The species as a whole survives. This is why mission planners keep drawing the ships, not because they believe the first crew will come home, but because they believe eventually humanity will spread. And spreading requires someone to go first, knowing they will not return. There is a strange kind of courage in this. The first interstellar crew will not be explorers in the traditional sense. They will be founders. People who leave their home forever so that someone, someday, might build a new home far away. Their names will be known on Earth for a while, then forgotten, then rediscovered centuries later when the colonies they founded grow large enough to matter. The Voyager probes launched in 1977 are often held up as a preview of this logic. They carry no crew, but they carry a gold-plated record with sounds and images from Earth, aimed at any intelligence that might eventually find them. the people who built the record knew neither they nor anyone alive would ever hear back. The project was a message to the future, a gift from a species that knew it would not itself be present for the reply. A crude interstellar mission is the same gift, multiplied. A handful of humans sent into the dark to become the ancestors of a civilization their home will never meet. They do not come back. They were never supposed to. That was always the price of the stars. And somewhere, in some not-too-distant decade, the first crew will strap in, take a last look at a blue dot on the horizon, and accept the trade.